In this video, we are going to be talking about exponential growth. And then the next video, we will talk about exponential decay. All right. So exponential growth occurs when a quantity increases, right? Growth is increasing by the same rate r in each time period t. And we model that by y equals a, and then in parentheses, 1 plus r to the power of t. Okay, so a represents the original starting amount, r represents the rate, and it's usually a percent as a decimal. So if it was 9%, right, I would take that decimal and I would move it 2 places to the left. So that would be 0.09 as a decimal. And then t represents time. So here's an example. It says the original value of a painting is 1,400 and the value increased by 9% each year. Write an exponential growth function to model the situation, then find the value of the painting in 25 years. Okay, so I'm going to have y equals a is my starting value. So that's the 1,400. Okay, then I've got my parentheses, and I always have 1 plus for growth. Okay, we'll see later for decay, that's going to be subtracting. Okay, then 9% is my r, and I need to convert 9% to a decimal. So I move the decimal place 2 to the left, and I get 0.09. Close parentheses, and then to the power of t. Okay, so this is the equation. T is the unknown value. That's like my variable. Okay, I don't know what t is. So now it's saying find the value of the painting in 25 years. Okay, so now when t equals 25, what am I going to do? Well, I've got y equals 1,400 times 1 plus 0.09 is 1.09, and then to the power of 25. Okay, and we can just do that in our calculator. So I do 1400 times 1.09 to the 25th power. And we get 12,072. So 12072. 12072. So that's how much money I have. Now, that's how much the painting is worth after 25 years. That's how much the painting is worth after 25 years. That's a pretty big jump. So next we're going to talk about compound interest, and basically what that means is interest on interest. Okay, and then I've got a question, is that good or is that bad? Well, it depends. What is compound interest? Okay, if you have a savings account or an investment account, it's the money that you're earning from your interest. That's a good thing. Okay, it's money that you're earning. You're getting 9% back every year. You're earning that into your pocket. But if a loan has compound interest, it's the interest that's charged on your interest. So that's more money that you're paying the bank or more money that you're paying the government. Okay, so then that, it would be a bad thing. So how could you figure out how much you're either earning or how much you're paying, right? So let's say you open a savings account, you have $1,000 in your savings account, and it goes up by 4% every year, right? If you didn't touch it, how much would you have in 5 years? Things like that. Okay, so compound interest formula is as such. So A equals P, which stands for the principal or the starting amount, parenthesis 1 plus R, which is the rate, as a decimal over n, which represents the number of times it's compounded per year. Okay, number of times it's compounded per year. And then t represents the number of years. So if I want to know over 5 years, things like that. Okay, so a couple of key words for compound interest. If it's being compounded annually, that means once per year. So my n is going to be 1. If it's compounded quarterly, that means 4 times per year. So my n is going to be 4. And monthly means 12 times per year. So n is going to be 12. All right, so next example. I want you to just write a compound interest function to model first, then find the balance after the number of years. So my first example is I've got 1,200 invested at a rate of 2% compounded quarterly. So that's what I'm going to use to write the equation. Okay, so I've got A equals that 1,200 is my principal, right? That's my starting amount. That's how much I put in my investments or I put in the bank account. And then I've got 1 plus, and then that rate as a decimal. So if this is my R, that means 0.02 would be my decimal. Okay, and then divide that by n, which is the number of times it's compounded. So if it's compounded quarterly, that means n equals 4. And then I've got n also in the exponent, and then I'm plugging in t for time. That's like my variable. Okay, so that is the compound interest function. Now let's find the value after 3 years. So I've got A equals 1,200 times 1 plus 0.02 over 4. Now 4 times 3. Okay, so we can type this into our calculator. We're just going to have to be careful for order of operations. So I've got 1,200 parentheses, 1 plus, and then in parentheses again, 0.02 divided by 4, and I have to close the double parentheses. Okay, now I go up into the exponent, and now I have new parentheses, 4 times 3, close parentheses. I technically don't have to do parentheses because mine is small, but if yours, it just puts a little arrow there, then you have to do parentheses. Otherwise, it will raise it to the 4th power, take that answer, and then multiply by 3, which is not what you want to do. Okay, so I have $1,274.01. $1,274.01. Okay, so I put in 1,200, and now after 3 years, I have 1,274, and I didn't even have to do anything, and I get extra $70. Okay. All right, one more. So another one. I've put 15,000 invest at a rate of 4.8% compounded monthly for 2 years. Okay, so that 15,000 is my principal at a rate of 4.8%. So R equals 0.048. Compounded monthly means my N is going to be 12. Okay, so I'm going to use that information. A, my amount is equal to my principal times 1 plus my rate as a decimal, 0.048 divided by N, which is 12, to the power of N times T. Okay, so again, when I'm just writing a function rule, I'm just writing those values. I'm not actually plugging anything in. Then I want to find after 2 years. And then I plug in t, and I would have a is equal to 1,500 times 1 plus 0.048 over 12 to the power of 12 times 2. Okay, and I can type that into the calculator. 1,500 parenthesis 1 plus parenthesis 0.048 divided by 12, double parenthesis close, exponent 12 times 2. And I get 1650.82. So I invested 15,000, and now I have 1,650 after 2 years. That's how exponential growth